Okay, so this page 8 in your notes, I think. Is that right? Turn to page 8. We're looking at the area of a regular polygon, and specifically for us, we're going to look at the equilateral triangle and the regular hexagon. So when you have a polygon, and you're working from the center of that polygon, there's two ways to draw segments from the center of that polygon to the polygon itself. And you can draw it from the center of your polygon to the center of a side, or you can draw it from the center of your polygon to a vertex. And are those the same length? No. And so we can't call them the same thing. It's not like a circle where we say, hey, there's one radius and that's all it is. So if we're going from the center of the polygon to the vertex, we call that a radius. So I'll put R there, or actually I'll just say radius here. Okay. If we're going from the center of your polygon to the center of a side, we call that an apothem. And you see it spelled right here. I'll put A, and I'll just point right there. Okay, that's your apothem. And so there's a little bit of vocabulary there. And so it's rephrased here. So the distance from the center of a polygon to a side is called the apothem. And the what if a regular polygon is the distance from the center to a vertex? Radius. Okay. Now, when we think about equilateral triangles, if I could spell equilateral triangles, hold on. All right. We know some stuff about them. What do we know about equilateral triangles? All sides are congruent. That's the definition. What else? All angles are congruent. And what else? The measure of those angles are 60 degrees. Okay. Good. And so if I give you a side length, we notice that, hey, if we cut this down the middle, something nice happens. It splits into what? Okay, it splits into two 30, 60, 90 right triangles. And we've worked with those before. There's some more, though, that we can talk about with these. If we start with an equilateral triangle, and let's put the center in now. Okay, and let's connect the center here. So here's our radius, and here's our apothem. What can you tell me about this triangle here? It's a 30, 60, 90 triangle. Again, where's the 30? This one's going to be 30 because it cuts the 60 in half. And this is 90, so this one's got to be 60. So it actually splits it into a 30, 60, 90. And then, in fact, it's important to know this. Let me move the A and the R here. Sorry. So if I go this way, if I draw to this vertex, we get the same thing. This is 30. This is 60 and 90. If we look at this apothem, this is a 30, 60, 90. Draw that vertex. This is 60, 90, 30. So we have this symmetry all the way around the circle here. And this is nice to know when we're working with equilateral triangles. Okay. So if you're able guess what you can say about all those 30, 60, 90 right triangles? They're all congruent to each other, right? So if you could solve one of those triangles, you know like everything you need to know about that whole thing, okay? Because the height of this thing is, God bless you, the height of this thing consists of two things. It consists of the yellow part here, which is an apothem, and the green part here, which is what part of the triangle? A hypotenuse. And so I could find the hypotenuse of any of these and know that that's the green part, and then the apothem's the yellow part. And so knowing those things about this can help you solve these. Okay, so let's take a look at some equilateral triangles. So number one here, 6 feet, what is that? The apothem's given to us. And so we would like the area of this, and area is 1/2 base times height. And right now we don't know either of those. We don't know the base or the height. That's okay. Because if we draw one of those smaller right triangles, we know it's a 30, 60, 90 right triangle. But you just got to be careful. Where do you put the 30? Where do you put the 60? Make sure you put it in the right spot. And towards the middle is the 60. And this is the 30. I'm going to make that a little bit bigger so we can see that. So here's 60, 30, 90, and we have 6 feet for the apothem, which is across from 30. And then we can draw our, we got to remember our 30, 60, 90, because this is going to be a scale of ours. And I'll put 1 across from 30. This is 2. This is root 3. And so we can use our 30, 60, 90 and scale it up to find the missing pieces. And so the hypotenuse is going to be what? 12. And the length across from 60 degrees will be 6 root 3. Okay? And so then you just got to relate these pieces back to our triangle to help us find the base length and to help us find the height. And just remember back here, this nice picture that how all those things are related. Okay? And if it helps you, you can even do this. Draw an equilateral triangle, connect the apothem. We'll draw those 6 triangles inside of it. And say, okay, all my apothems are congruent. All the radii are congruent. And then all these pieces are congruent. Okay, if that helps you get a little visual. Okay. And in our picture here, the apothem was 6, so I'm going to put a little 1 mark there. The hypotenuse was 12, and that would be 2 marks. That's the radius. And then this would be our 3 marks, right? And so you could see my base, I have 2 of the 3 markers, right? So this is 6 root 3 here, and I have another 6 root 3 here. And so I need to add those together to get my base length. It's 1/2. What's 6 root 3 plus 6 root 3? 12 root 3. And then you can see the height as a 1 marker and a 2 marker. So that's an apothem plus a radius. And so my apothem's 6. What's the radius right here? 12. So apothem plus the radius, 6 plus 12, gives us the 18. All right? So just remember that the height of the triangle is an apothem plus a radius. And then you got your base. And now we have the numbers we want. We can crunch those numbers with a calculator, or we can leave it in another form. So this is going to be 9 times 12 root 3. I got 9 because I took half of 18. 9 times 12 is 108 root 3. So if I say don't round anything, I want the perfect answer. That would be your perfect answer. with square feet. But if I say approximate it, then you're going to use your calculator. Anybody have that? What does that come out to be? Approximated. 339.29? Okay. So I want you guys to try number 2, just like we did number 1. You try number 2, see if you could find the area, just like we did together. Okay, so here they give us the apothem again. And no matter where we write it, so because that's 18, you know, if I draw the apothem here, that's also 18. If I draw the apothem here, that's 18. Okay, but let's look at this right triangle here. Okay, we got 18. Here's our radius and half of a base length. Okay, call that x. And so I'm going to take that triangle and make it a little bit bigger so we can work with it. It's a right triangle. It's 18. Now we need to know where to put angles. Where's the 30 go? Where's the 60 go? And in an equilateral triangle, this whole thing is 60 each. And so this is cutting the 60 in half. And so 30 goes across from 18. 60 goes here. And so if we think about our 30, 60, 90 right triangle, we have 1 across from 30. 2 is our hypotenuse, root 3 across from 60. And so how do we, so what's our radius going to be? Ours is going to be, I'm going to scale it up. So this, how do I go from 1 to 18? I multiply by 18. So I'm going to multiply the 2 by 18. I get a radius of 36. And for x, I'm going to multiply root 3 by 18, scale that up to 18 root 3. Okay. So all around this triangle, even this piece is 18 root 3. This is 18 root 3. You could just keep going around, 18 root 3, and so on. Okay, and the radius we said is 36, and this height here is 18. And so we see our height of our triangle is the apothem plus the radius, and the base is going to be 18 root 3 plus 18 root 3. And so now we're able to say the area is 1/2 the base, 18 root 3 plus 18 root 3. That's our base. And then times our height, which is 18 plus 36. Okay. And then we're able to work through that. 1/2 36 root 3 times 50, what's that? 54. Okay. And if we approximate that, what does that come out to be? What'd you get, Chase? 1,683.55. And we're looking at square millimeters. Are we all getting that? Okay. So that's dealing with it, finding the area of an equilateral triangle. Okay. Now let's talk about regular hexagons. So the word regular, when we're talking about polygons, regular means all the side lengths are the same, all the angles are the same as well. Okay, that's when we use the word regular. So regular hexagon. Okay. Okay, so if all the side lengths are the same and all the angles are the same, first thing I want you to know is, well, what are the angles? Okay. Yeah. Not quite. Here's what I'm going to do to help you see what all the angles are. If I put a circle if I around this right through the vertices, okay, and because these are all become chords of that circle. We're going to see that right in a second. So all those chords, because all the chords are the same, we can say that all the measures are the same. And how many, how many parts of that circle are split up? Or how many chords are there? 6. And if a full circle is 360 degrees, and we're splitting that equally into 6 parts, what's each part going to be? So this is 60 degrees. Each part here is 60 degrees. Okay. Now let's just focus in on this part here and this part here. That's an inscribed angle intercepting an arc of that circle, right? And it intercepts the arc of these 4 angles. So what's the measure of that intercepted arc? 240 degrees. So what's the measure of my inscribed angle? Half of that, which is 120 degrees. Okay, good. So all of these, you want to know that, all of these are 120 degrees. Okay. So next, if we, I'm going to draw another, draw another hexagon. So if I go from the center now and draw all the radii, okay, going from the center to the vertices. So we know all these lengths are the same, right? We're going from the center into a regular polygon. And what happens is we end up with 6 congruent triangles here. And it splits that angle in half. This becomes 60 degrees. And it's isosceles, so this is 60 degrees. And then this has got to be 60 degrees. So we actually end up with equilateral triangles. Okay? And we just talked about how to find the area of an equilateral triangle. And so what we want to know here is that the area of the hexagon is equal to the 6 times the area of these equilateral triangles. Right? So if we can find the area of one of the equilateral triangles and then multiply it by 6, then we're good. And so that's going to be our method. So let's go look at a problem now. Number 3 here. We have a hexagon. Here's an equilateral triangle that we want to find. If we can find the area of that and then multiply it by 6, then we're good. So I'm going to call this triangle ABC. And I'll put even point D here as well. Okay. So ABC, so the area of my equilateral triangle, ABC, is going to be 1/2 base times height. Do we know any of those? We know the apothem, which is the height. Okay, so we know it's 1/2 the base times 5. Okay, so we can find the base length, then we're good. So this is an equilateral triangle, so we know that angle A, right in here, or angle BAD is 60 degrees. We know, so this is a 30, 60, 90 if we cut it down the middle, right? And so I could redraw it here. This is A, D, B. and this is 5, this is 30, this is 60, okay? And we can use what we know about 30, 60, 90 right triangles to help us find these lengths. So our 30, 60, 90 right triangle has a hypotenuse of 1, hypotenuse of 2. Across from 30 is 1, and across from 60 is root 3. Not as easy to see. How do we scale it from root 3 to 5, is it? That's okay. So sometimes it's easier to think of scale factors. Other times it's just easy to say that these are proportional. And so let's say, okay, this is our radius here. Let's go after the radius. So I know 5 corresponds with root 3, so I'm going to say 5 over root 3. And then the radius corresponds with 2. I'm going to put r over 2. And then I can cross multiply and solve for r. So r times root 3 is 10. And I divide by root 3 and I get r is 10 over root 3. And we're in the habit of rationalizing these. So I'm going to multiply top and bottom by root 3, and so I get r is 10 root 3 over 3. Okay. But we didn't even want r. Why did I solve for r? Because we wanted the base length, huh? But r is the base length because it's an equilateral triangle, right? Right? Think about it. This whole thing is an equilateral triangle. So if this is 10 root 3 over 3, so is this piece here 10 root 3 over 3, and so is this piece here. Okay? So the radius of this is the base of our triangle too, because it's an equilateral triangle, so we can keep that in mind. So I wasn't thinking. I just solved the radius, and then I thought a little bit and said, okay, actually that was fine. Okay, so I wasn't intending to do that, but it worked out nice. Okay, so now this is going to be 1/2. Our base, 10 root 3 over 3 times 5. And that just gives us the area of the triangle. So how would we find the area of the full? Multiply that by 6 because it's created by those 6 equilateral triangles. Good. So that's the area of the triangle. And so then the area of our hexagon is going to be 6 times that. So 6 times 1/2 times 10 root 3 over 3 times 5. Okay. What does that come out to be? What's that? 86.6, and we're looking at meters, square meters. So if we want, we can go back to what we were drawing out here and make another connection. So we found that this is 6 times the area of a triangle, but we found that the area of the triangle is 1/2 the base times the height of that triangle. And what did we say the base was equal to? The radius. What would we say that, and what would the height be? It's the distance from the center to the middle of the side. That's called the apothem. You don't have to memorize this, but I'm just making some connections to you. So we could say it's 3 times the radius times the apothem. We want to make the connection, right? So I want you now to go ahead and find the area of number 4. Okay, then anybody have, or can anybody, I don't want the final answer, but just lead me through what you did to get there, Elena. Okay, so do you like the apothem right here? Okay. Did this right here? Okay. Good. Good. So we already have that. So this is 11, this is 11. Okay, so you're just using, okay, so this is a right triangle. So you said 11 squared plus, I'll put a squared for the apothem, equals 22 squared. So let's see, 121 plus a squared, 22 squared, what'd you get? 484? And 363? Okay. Area of the triangle? Area of the triangle is 1/2. So we're talking the equilateral triangle. 1/2 base 22 times the height, square root of 363. And that's 11 root 363. And then the area of our hexagon, 6 times that, so 66 root 363. Nice. And that came out to be about what? And we're talking square yards. Now that's a different way than I was thinking myself. Did anybody do it differently? You got the same thing? Yeah. So what'd you do? Okay. Mm-hmm. Okay, because this is a 30, 60, 90, right? And so if we have our 30, 60, 90, we have length 1 here, length 2 here, root 3 here. And so we can relate 1 to 11, right, by scaling it up by 11. So our apothem, in this case A, would be 11 root 3. And then you did what Elena did. Or Lena. Sorry. Lena did, right? So that means if we simplify 363, we should get 11 root 3. And you can try it out, and actually it works out that way. Okay, this is good. So I'm going to stop there with the notes.